So hello everyone, welcome back to our Stereochemistry lecture series. So this is the lecture 5. So in this particular lecture series we are talking about the representation of chiral compound. So I would suggest that please very cautious about this particular lecture, because in this particular lecture we'll see that how can we represent a 3D geometry of a stereochemistry in our 2D plane, that is our copy or notebooks. Okay, so first let us understand that different projection formulas. So basically there was a widely used projection formulas, there is a Fischer projection formula, Sawhorse projection formula, Neuman, flying wedge and Zig Zag projection formulas. So chiral compound can be represented by this particular projection formulas and it will be very interesting. Okay, now first talking about the Fischer projection formula. Fischer projection is a representation of 3D molecule into 2D plane, and it is represented by two vertical line that is perpendicular to each other. Okay, and Fischer projection will always represent the eclipse configuration, that is not important. So see, in our one chiral center the Fischer projection can be shown something like this, where this particular intersection shows the chiral carbon which is in the plane of paper. Okay, and this particular horizontal bond, for a vertical bond, this particular vertical bond, it is the main chain. Okay, the main chain of a molecule is represented by a vertical line from top to bottom, and this particular vertical line represents the bond which is below the plane of paper. That means this particular bonds are away from the observer. Okay, like if I am observing something here, if I am observing this molecule something here, then vertical bond contains group are always be away from the observer, and this bond is called a horizontal bond, and this particular horizontal bond represent the bonding bonds pointing towards the viewer. Like these two, if we see this particular compound from this particular angle, then this particular chiral center is present in the plane of paper. These two group as well as these two bond are away from the observer, and these two groups will be the closer to the observer, or it will be the above the plane of the paper, and these two vertical will be below the plane of the paper, and the carbon center or the chiral center present in the plane of the paper. So this is a normal 3D Fischer projection representation. Okay, now there is certain rule associated with the Fischer projection formula. First of all, that a Fischer projection can be rotated by only 180 degrees without changing the configuration of the molecule. Like 180 degree shuffling is okay, but 90 degree and 270 degree if we rotate, then what happened, the absolute configuration will be changed. Like if we rotate by 180 degree, then if the molecule is initially R configuration, that will become the R configuration. However, by 90 degree to 270 degree rotation leads to R to S configuration, means the absolute configuration is changed, so it will be not allowed. And also interchange of two substitution represent the interconversion and interconversion of the configuration. So to keep the same configuration, you must take an even number of swaps. Okay, that means if you change this particular groups, like here to here, then you have to change this only. If you change only this particular groups, one pair of groups, then you will be this particular two interchange of this groups, then it will be change the configuration of the overall molecule. So you will go for an even number of swaps. Okay, and the Fischer projection can be reflected through a horizontal or vertical mirror to obtain its enantiomers, and the chiral center is changed from R to S. Like if we put a mirror, so it will be shown a non-superimposable mirror image relationship, and it will be a enantiomers to each other. Okay, and also there is another thing like swiping method. Like if you want to keep this group intact, then you have to change something like this. Okay, you have to change this group something like this without changing the configuration. Now here in this particular cartoon diagram, you might find little bit of confusing. So when we are discussing about some question answers, then I will show that how can we change or interchange the groups there effectively without changing the configurations. Okay, so now let us talk about the different configurations, that is Sawhorse projection. Sawhorse projection is suggested there is a minimum 2 chiral center is required, and it is a representation of like letter Y, and this particular group is something like this. There are 2 chiral center is there. Here this particular group is the front carbon and this will be a back carbon. Okay, and here it is written an eclipse structure. Eclipse structure suggests that this particular 2 groups are actually in the same plane, and due to this it is called eclipse, but here all the groups are present in the different planes, so it is a staggered structure, and the staggered structure is usually much more stable. Because of that, in the case of eclipse structure there is a van der Waals interaction or Blackpool interaction takes place, and that's why it will be less highly energetic, so it will be less stable structures. Okay, and the bond angle between this is 120 degree. Okay, and there is another interesting thing that I want to tell you, that why the eclipse and stagger structure has been observed. Because in sp3 carbon center there is a option that in case of an sp3 carbon, this carbon-carbon bond rotation, just I have a highlight here, this particular carbon-carbon bond is able to rotate. Okay, so that's why actually this particular group is rotating without changing their absolute configuration, and it will become a different conformers. So we will discuss it elaborately during our conformational analysis part. Okay, so just remember this particular thing for a Sawhorse projection. Similarly, we can observe in the Neuman projection also. Neuman projection is nothing but a Sawhorse projection, but just we can squeeze this particular compound. So here is also bond is viewed from one end. Like in Sawhorse projection, we have seen the bond from here itself. Okay, in Sawhorse projection, but in the case of Neuman projection, we have observed this particular chiral center from this end, this line, through CC double bond, and from there, so there is a representation formula something like this, like the front carbon has been represented by a dot and the black carbon represented a circle, and here we can see this eclipse structure and the stagger structure difference. Here the eclipse, you can see there is the interaction was there between these 2 groups, and that's why actually it will become less stable compared to the staggered. Okay, and this particular Neumann projection is very important during conformational analysis, but not important in the determination of absolute configuration, but it will be very important in our conformational analysis. Now there is another projection, it is a flying wedge or wedge test projection, that can be very important in to determine the RS configuration or the absolute configuration as well as the representation. You can find mostly Fischer or flying wedge representation in our organic compounds. Okay, and it is the most accurate representation, I would say, because it will be clearly shown the 3D geometry here. Okay, so here minimum 1 chiral center is required for this projection, just like Fischer. Fischer we can go up to 1, 2, 3, 4, 5 anything, but here not, usually 1. Okay, so this particular 2 bonds are present in the plane of paper. Now here the interesting representation of the bonds. Now it is, this particular bond is called a dashed bond. Now dashed bond represent the group that is below the plane of the paper. Okay, and this group is called a wedge bond. Wedge bond, it is determined that this particular group is present above the plane of the paper. So similarly, if we do this wedge test representation of Fischer compound, then we can found that vertical bond is nothing but this. This is our center, and our horizontal bond is So the Fischer representation of something like this, I don't think that it will be visible due to my screen. So the Fischer representation in terms of resistance should be this. Okay, so this particular means this vertical bonds we are already discussing the Fischer configuration, that in vertical bond it is away from the observer, so it is the below the plane, and the horizontal bonds are near to the observer, so it is called a vertical plane. Is near the observer, so it is above the plane, so it will be represent something like this. So this is the terms of flying wedge. Now there is another representation, that is the zigzag representation. It is mainly used for the carbohydrate or the long chain compound which contains 3 or more chiral center. So the rule of the zigzag projection is longest alkene chain was present in plane. So here the longest alkene chain is the vertical bond, so it will present in the plane, and in this particular representation hydrogen is usually not shown, and it is an upgradation of Fischer and flying wedge representation. So it is represent like this. So how to interconvert this we will discuss in our next class. Not this particular class we are discussing, just I want to show that zigzag positioning something like this. So in this particular lecture we have learned 5 different projection formulas. I hope this will be clear. So in the next lecture we are talking about the interconversion of projection, how we can interconvert from a Fischer to Sawhorse, Sawhorse to Neuman, and Fischer to flying wedge, and vice versa. So stay tuned for that particular lecture. So thank you for listening.